Hey everyone, welcome to our next video. This one is going to be over 5.2. Let me go ahead and go over to our notes section. Alright, so this is 5.2, which is right triangle trigonometry. So the first thing that I'm going to discuss here is the relationships of sine, cosine, tangent, and also the reciprocals of those. So let's go over some things for a moment. Hopefully this is a little bit of review, but in the past you may have learned something called SOHCAHTOA. What this is an acronym for is that sine of an angle is equal to the opposite side over the hypotenuse. Cosine of an angle, I don't really like that S capitalized, there we go. Cosine of an angle is equal to the adjacent side over the hypotenuse. And tangent of an angle is equal to your opposite side over your adjacent side. And so if this is not review, let me give you a little bit more background. When you have a right triangle, and we'll put our angle down here. The reason I'm putting it there is because whenever we talk about angles being in standard position, we always want them touching the x-axis, or in this case, just the horizontal. And so that's why I'm putting my angle right there. So across from your right angle is what we call our hypotenuse. Across from the angle that we are looking at is my opposite side, and then touching the angle is my adjacent side. So sine, cosine, and tangent are, here let me write the actual, so this would be sine, this is cosine, and this is tangent. Sine, cosine, and tangent, what they are is they represent a ratio of one of the sides of the triangle to another. So for instance, sine of an angle is the opposite side divided by the hypotenuse. Cosine of an angle is your adjacent side over the hypotenuse, and tangent of any angle is your opposite side over your adjacent side. The angle there is very, very, very important. So let me tell you something. You never ever want to write something like this. You never want to say sine is equal to, let's say, 3 over 5. I'm just making something up there. I'm missing an angle on that sine. This is really bad notation. This can't happen because sine doesn't exist without the angle that you want to talk about. Because if I don't have an angle right here, oh, I didn't mean to have the eraser on. If I don't have an angle right here, then I don't know what my opposite side is, right? So I need an angle to be there. Because if I put my angle up here, then my opposite side is now here instead of that being the adjacent side. So the angle is very, very important to be with the sine, cosine, tangent. Now we also have what we call the reciprocal functions, but they are cosecant, and cosecant is the opposite of sine. So cosecant is the hypotenuse side divided by the opposite side. We have secant, which is the hypotenuse divided by the adjacent side, so that's the opposite of cosine. And we have cotangent, which is the adjacent side over the opposite side. And I'm going to write the real names underneath them. So this is cosecant, this is secant, this is cotangent. And so cosecant is the opposite, meaning it's just the flip or the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. Again, it's very, very, very important that we have the angle on there. You never want to just write cosecant and not have this angle in here. Something else to remember is that angles are either in degrees or they're in radians. So you should never really be putting in something like, so this happens a little bit later, but I'm just going to talk about it now just because it comes up. My word went away. Okay. I just want to discuss this for a moment. If I tell you something like sine of an angle is 3/5, this is not the same thing as you writing sine 3/5. But this happens a lot in this class, especially when we start doing identities and stuff like that. So make sure whenever you do in the parentheses of sine, meaning where the angle should be, it should either be in radians, which means it probably has pi within it, or it has a degree symbol. A ratio like this, 3/5, that's not an angle, so it can't go in the parentheses like that. It can't be the angle in sine. I hope that makes sense, but it's just kind of some notation issues. The other thing about right triangles is that the Pythagorean theorem holds true. So something we're going to work with a lot is a squared plus b squared equals c squared. That is the Pythagorean theorem. All right. Good to know. And just to, say this one more time, this is only true for a right triangle. So this must be a right triangle for all these other things to be true. So if we don't have a right angle, sine is not opposite over hypotenuse. The reason for that is because a hypotenuse is the side across from the right angle. So if we have no right angle, we have no hypotenuse, which means Pythagorean theorem doesn't hold, and the rest of this SOHCAHTOA stuff does not hold. That's good to know for when we do test 3. For a while in this class, we'll be working with right triangles. We're really not going to stop working with right triangles until test 3, so you don't have to worry about it for a moment. All right. Also, I do want to make a little note here. Also, if a denominator at any point is 0, then we say undefined. So if at any point we plug something into one of these ratios and we get that a denominator is 0, we're going to say that it's undefined at that spot. All right, let's go ahead and talk about one more thing. Standard position is going to mean that our angle will always touch the x-axis. And this is just for as we start working with maybe more quadrants. We might not do that right this moment, but just for later. So when we work in quadrant 1, our angle is here in standard position. If we work in quadrant 2, we're going to put our angle here. Quadrant 3 here. Quadrant 4 here. And the reason I bring this up is because you can make a right triangle in each of these quadrants. And so sometimes we'll need to do that. We'll have to make ourselves a right triangle. And so it's good to know where your angle should always be. Again, that comes up a little bit later, but it's just a good time to discuss it. All right, let's go ahead and just work with that sine, cosine, and all of those relationships. So example 1, I'm going to say find the exact values of the 6 trig functions for angle theta. And here's our triangle. I'm going to say this is theta is here. This side is square root of 3. The hypotenuse is 7. And I don't know the other side. So the first step in this is I need to know what this side is. So I need to know this missing side. To do that, we can use Pythagorean theorem. So if you're not familiar with Pythagorean theorem, it says a squared plus b squared equals c squared. Let me go ahead and write some more stuff first. So first we find missing side. And so we're going to use a squared plus b squared equals c squared to do that. So the a and the b have to be the legs of your triangle. They are never the hypotenuse. C is your hypotenuse. Now, it doesn't really matter which one you call A, which one you call B. I often make the A value like the horizontal and the B the vertical. And that's just because it helps me be consistent for stuff that'll come up a bit later. So that's just more of a personal preference. So if I plug in here, so if I have my A is square root of 3, and that's squared, plus b squared, I don't know what that is, but I'm trying to find it, equals c squared, so that would be 7 squared. I have only one unknown now, so I can solve this for b. So first I'm going to simplify. Square root of 3 squared is 3. 7 squared is 49. I'll subtract 3 from both sides. So I get b squared is equal to 46. So then b is the square root of 46. Now be careful here. Technically, whenever you take a square root, this becomes plus or minus. Because it didn't tell me what quadrant we're in, we're just going to assume we're in quadrant 1. So this is just going to be a positive root 46. Now I'm going to write all of my trig functions. So sine of an angle, remember we need to have that angle there, is my opposite over my hypotenuse. Cosine of an angle is my adjacent over hypotenuse. Tangent is my opposite over my adjacent. And then I'll have to do the other functions as well, the reciprocals. So cosecant is the opposite of sine, so that's going to be hypotenuse over the opposite. Secant is the opposite of cosine, which is the hypotenuse over the adjacent. And cotangent is opposite of tangent, so that's going to be my adjacent over my opposite side. So if I look at my triangle, this is my hypotenuse. Opposite my angle means across from it, so that's my root 46. And my adjacent side is the one that touches the angle, so that's going to be square root of 3. So now I'm just going to do a bunch of plugging in. So my opposite is square root 46 over my hypotenuse, which is 7. Then I have my adjacent side over hypotenuse. That's going to be square root 3 over 7. My opposite over my adjacent, so that's going to be square root 46 over square root 3. Hypotenuse over opposite, so that's 7 over root 46. Hypotenuse over adjacent, 7 over square root 3. And adjacent over opposite, so that's square root 3 over square root 46. Okay, I'm fine if you leave your answers like this on an exam for me, but just be aware that the homework is going to ask you to rationalize, because that is considered simplest form. It's something that I don't necessarily take off for, but it is nice if you can do it. So rationalizing means to get rid of radicals in the denominator. So to do that, I'll have to multiply this one by root 3 over root 3. So that's going to give me square root 46 times square root 3 over 3. Let me think for a moment if square root 46 can simplify at all. It cannot. I was just trying to think for a moment if it could reduce. So it can't. So that's going to be square root 138 over 3. This one I have to multiply by root 46 over root 46. So this would be 7 root 46 over 46. This one I'll multiply by root 3 over root 3. This is 7 root 3 over 3. And this one, root 46, so I get root 138 over 46. So just be aware that the homework is going to ask you to rationalize. If you are struggling with rationalizing, you can look up a quick video on it. This is more of an algebra topic. Something else to watch out for, if these radicals can simplify at all, like meaning they have a perfect square in them, so like if I can split 46 into a perfect square, then I would want to do that. That's what I was checking for earlier, but 46 doesn't split up in any perfect square, so it would just stay as is. Okay, let's go ahead and go on to our next problem. Our next one says, if cosine of theta is equal to square root 13 over 4, find cotangent theta. This is a pretty common idea that will happen later in the course. I'll tell you that this section is very important for the entirety of trig. It has a lot of fundamental topics inside of it. So if I'm telling you that cosine of an angle is equal to some ratio, what I'm really telling you here is I'm telling you two sides of the triangle. So if I make this into a triangle, cosine is my adjacent side over my hypotenuse. So when I tell you that cosine of an angle is some ratio, I'm giving you two sides of the triangle. So I'll put my theta at the bottom here because that's kind of what we usually do because we want our angles to be in standard position. Now for this problem in particular, let's say you put your angle up here. You would not have you wouldn't run into an incorrect answer or anything. It would be best if you put it at the bottom, but it would be okay at the top. It won't create a wrong answer. My adjacent side is touching the angle, so that's going to be down here, square root 13. and my hypotenuse is 4. And I'm looking for cotangent of my angle. So cotangent of an angle is the adjacent side over the opposite side. I already have my adjacent side, but I don't have my opposite. So I'm going to ask you, how can you find the opposite side for this triangle? Hopefully you said Pythagorean theorem. So if I use Pythagorean theorem here, so I need to find the opposite side. So I'm going to say I have a squared plus b squared equals c squared. So square root 13 squared plus b squared equals 4 squared. 13 plus b squared equals 16. Subtract 13 on both sides. I get that b squared is equal to 3. Take the square root. I get b equals square root 3. Now again, if it had said something about being in a different quadrant, we would want to consider maybe having a negative b value. But right now in this section, we're really just working in quadrant 1. I'll do some problems later that change the quadrant. I'll tell you that on a test problem, I like to always define what quadrant you're in. I don't like to ever leave it up to assumption. So now for my cotangent, I have both my sides that I need. My adjacent is square root 13, and my opposite is square root 3. Again, we do need to rationalize this, so if I multiply by root 3 over root 3, I'm going to get root 39 over 3. And so this would be my final answer for this one. So this is a really good idea that we will use like throughout the whole course of just me giving you one of the trig functions and you have to use that to find a missing side. And then maybe also find another trig function. Now we're going to look at some special triangles. So some special triangles that we're going to see often is we're going to see 45, 45, 90 triangles. And we're going to see 30, 60, 90 triangles. Those are your special triangles that we will look at. And so first of all, I want to define a few things for you, kind of show you where some of this comes from. If I start off with a box, and let's say that every single one of these sides is just 1. If I split this box in 2, right down the middle, that would break each of these angles up in half. So this would be a 45-degree angle, and this would become a 45-degree angle. This is now what we're going to be looking at. So this is how we get the 45, 45, 90 triangle. And just a reminder, triangles always add up to 180 degrees, so that's why we need 180 degrees in our triangle. So if both of these legs of my triangle is 1, I need to find my hypotenuse. How do I find my hypotenuse? How do I find the missing side of a triangle? I use Pythagorean theorem, so I'm going to say a squared plus b squared equals c squared. So 1 squared plus 1 squared equals c squared. So I get 1 plus 1 equals c squared. 2 equals c squared. So c equals square root of 2. So this side, this hypotenuse would be square root of 2. Okay. let me explain to you why we call this a special triangle. What is interesting about this is it tells us what our sine, cosine, tangent, all of them would be for 45 degrees no matter what. So let's say that we have our triangle to have slightly bigger sides. Let's say I make this side a 3 and this side a 3. What you will see is that this hypotenuse would become 3 square root 2. Let's say we get bigger sides than that. Let's say I do 80. This would be 80, this would be 80, this would be 80 square root 2. And so what's going to happen here is the ratios of sine, cosine, tangent for 45 degree angles, it won't matter how big or small that triangle is. The answer is going to be the same no matter what. So let's look at this for a moment. Let's look at sine of 45 degrees. So instead of just calling the angle theta like I did earlier, I actually have given it a measurement. So I'm looking at the 45 degree angle. Really, you can look at either one, but as you all have probably seen and hopefully caught on to, I always like my angle to be at the bottom, touching the horizontal. So sine of 45 degrees. So sine of 45 would be my opposite over my hypotenuse. So that'll be 1 over square root 2. Rationalized, this is the same as square root 2 over 2. Okay. Great. Now let's do cosine of 45 degrees. I have no idea why it's writing in bold. Sometimes it just does that. It must be how I hold the pen, but I don't know what I'm necessarily doing when it happens. Now cosine, remember, is your adjacent over your hypotenuse. My adjacent side touches my angle. So it would still be 1 over square root 2. Rationalized, root 2 over 2. If we look at tangent of 45 degrees, this would be my opposite over my adjacent, so 1 over 1, so just 1. This is going to be something we need to memorize for the rest of trig. So we're going to come back to this over and over and over again. The fact that sine of 45 is square root 2 over 2, cosine of 45 is root 2 over 2, and tangent of 45 is 1. We're going to come back to this all quarter, okay? I'm going to, at the end of this, I'll kind of show you another way to hopefully remember this. Hopefully a quicker way, because there's going to be more to learn, to remember as well. The nice thing is it's only the second section, so you've got a while kind of to memorize it. Now, if we go ahead and look at the reciprocal functions as well, so cosecant of 45 degrees would be root 2 over 1, or just root 2. Secant of 45 degrees would be root 2 over 1, or just root 2. Cotangent of 45 degrees would be 1 over 1, so just 1. I don't think it's necessary to memorize those, because as long as you know sine, cosine, and tangent, you can always know that the reciprocal functions are just the flip of that, just the reciprocal of them. So it's not really necessary to have them memorized. So this is the 45, 45, 90 triangle. Let's go ahead and learn about our other important triangle, which is the 30, 60, 90 triangle. The 45, 45, 90 came from a box. This one actually comes from an equilateral triangle. An equilateral triangle means that all the sides are the same, and so all the angles must be the same as well. 180 divided by 3 would be 60 degrees. So in an equilateral triangle, all of your angles are 60 degrees. If I make this into a right triangle that I want to look at, I can split it down the middle. And so hold on for a moment. I told you that all the sides must be equal in an equilateral triangle. I'm going to make all of my sides equal to 2. Now, the reason that I'm choosing 2, I could have chose 1, but it would make us have to deal with a little bit more fractions. It really won't change the outcome, though. If we really wanted to, I could make all the sides here 134, and I would still end up with the same answers at the end of what I'm about to do. Like the sine, cosine, tangent, all of that would end up the same way. Same thing up here. Like if I had used, you know how I did that 80, 80, and 80 root 2? We could have used those as my sides. The sine, cosine, and tangent would have ended up the same things. So I'm using 2 because it'll just make it a little bit easier to work with. All right, so if I split this into like 2 triangles down the middle, that'll give me a right angle right here. That would mean that the 60-degree angle up top is now 30 degrees because it's split in half. And then this side would now be 1 since it's half of 2. So let me go ahead and draw this new triangle. That way we can just see it a little bit better. So this is now 30 degrees. This is 60 degrees. My hypotenuse is 2. My adjacent side down at the bottom, or whatever you want to call it for the time being, that is 1. Now, to find that other missing side, I'll have to use Pythagorean theorem. So I would have a squared plus b squared equals c squared. So this is like my b over here. So it'd be 1 squared plus b squared equals 2 squared. 1 plus b squared equals 4. Subtract my 1, which will give me b squared equals 3. So b equals square root of 3. This is the 30, 60, 90 triangle. And so just like before, we're going to do the sine, cosine, and tangent of my angles. So first, let's look at sine of, since the 60 is at the bottom, I'm just going to do that one first. So sine of 60, we'll do cosine of 60, and we'll do tangent of 60. If I'm looking at the 60 degrees, then this is my opposite, this is my adjacent, and this is my hypotenuse. So I'm looking at sine of 60 degrees. So my opposite side across from 60 is square root 3. My hypotenuse is 2. This means that sine of 60 degrees is square root 3 over 2. And that's always. Cosine of 60 degrees would be 1 over 2. Tangent of 60 degrees would be square root 3 over 1, or just square root 3. I'll do the reciprocals as well. So cosecant of 60 degrees, secant of 60 degrees, and cotangent of 60 degrees. Cosecant would be 2 over root 3. Rationalize, this is 2 root 3 over 3. Secant would be 2 over 1, or just 2. And cotangent would be 1 over root 3. Rationalized would be root 3 over 3. Now I'm going to look at my 30-degree angle. Now for my 30-degree angle, since it's up top, you're welcome to redraw the triangle. I'm just going to label it a little differently. So if my 30-degree is at the top and that's the one I want to look at, that would mean that this side is now my opposite side. My square root 3 is now my adjacent side, but my hypotenuse is still 2. So I'll do sine of 30 degrees, cosine of 30 degrees, and tangent of 30 degrees. I'll also go ahead and do the reciprocals as well. Remember, sine is opposite over opposite over hypotenuse. So my opposite side here is 1. My hypotenuse is 2. Cosine is adjacent over hypotenuse, so that'll be square root 3 over 2. Remember, the opposite and adjacent sides, they're just based off of where your angle is. So that's why they're a little different now that we're looking at a different angle. Tangent of 30 degrees would be 1 over square root 3. Oh, I didn't write. Hold on, y'all. My pen isn't working. There we go. Cosecant of 30 would be the opposite of sine, so that'll be 1 over 2. 2 over 1, so just 2. Secant would be 2 over root 3, or 2 root 3 over 3 if you want rationalized. And cotangent of 30 would be square root 3 over 1, so that's just square root of 3. Something I hope you are noticing here is that the sine of 60 is the same as cosine of 30. The cosine of 60 is the same as sine of 30. And you can kind of just see the other relationships happening here. It's just because all that changed is the opposite and the adjacent side. So it just kind of flipped it a little bit. Okay, you do need to remember all of these. However, I would never memorize the reciprocal functions, because as long as you know sine, cosine, and tangent, you would just flip it to get cosecant, secant, and cotangent. So I wouldn't worry about memorizing those, but you will need to memorize the sine, cosine, and the tangent. There are a few different ways that people may want to memorize these. Maybe you are good at just doing it straightforward and you just memorize them as I've written them. Some people like to memorize the triangle, so just knowing that the triangle itself is the 30, 60, 90. The 1 is across from the 30. The 2 is the hypotenuse. The square root 3 is across from 60. And then just getting whatever they need from there. And also, same thing with the 45, 45, 90. Some people may just want to memorize that triangle itself. I'll give you another way to remember these, and this is probably my preferred method. So if I'm going to draw us a table. So if you want to follow along with me, I have 30 degrees, 45 degrees, 60 degrees. Then at the top here, I'm going to write that I have cosine of an angle, and I have sorry, did I say that right? Sine of an angle and cosine of an angle. Draw myself some lines in here. I'll put tangent into my table as well. The next step of drawing out my table is I'm going to put an empty square root over 2. And we're going to fill in the square root at the end. I'm not going to do my tangent side yet. This is only for the sine and cosine. I'm going to leave my tangent for the end. So go ahead and pause the video and draw what I have so far. Empty square root over 2 on everywhere on sine and cosine. You want to make sure you watch for the next part. So for sine, I'm going to count from 1 to 3. 1, 2, 3. So if you look back, square root of 1 is just be 1, so this is 1 over 2. Sine of 30 is 1 over 2. Sine of 45 is root 2 over 2. Sine of 60 is root 3 over 2. For your cosine, you're going to flip and you're going to go 3, 2, 1. And just a reminder, square root 1 over 2 would just be 1 over 2. So if you can know how to draw out your table, this can be an easy way to help you memorize these important angles. Now, tangent. So what I do here is I remember that sine is my opposite over my hypotenuse. Actually, let me write it. I'm going to write it up at the top. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So all of these 2's here, those are all the hypotenuses. So I'm not going to need them for my tangents. I just want the numerators. So tangent of 30 degrees, I'm going to take my numerator for sine over my numerator for cosine. So this would be 1 over square root 3. Rationalized, this would be root 3 over 3. For my 45, I'm just taking my numerators. Square root 2 over square root 2. Anything over itself just equals 1. For the 60 degrees, I'm taking my square root 3 over 1, so that's just square root 3. So even here, this kind of tells you that you really only need to memorize sine and cosine. And then you can use those to just go get tangent. Now, I really can't stress this enough to you, but you do need to memorize all of these. If you do not, you will have a hard time in trig, because we're going to use this the whole way. So take some time to remember these things. Now again, the table is just a way to memorize everything that I've done in the last 20 minutes probably. Just the whole specials triangle section. So instead of maybe having to memorize the triangles themselves and all of that, I'm just giving you the table to help you memorize it. It's up to you what you like. But I had to show you the triangles to just show you where it all comes from. Alrighty. I'm going to move on from this, and now we're going to do an example with it. So let me look at what number we're on. This would be example 3. So I'm just going to say simplify the following. Part A, we're going to have tangent 60 degrees minus tangent 30 degrees. Part B, I have 2 sine pi over 6 cosine pi over 6. And so I'm going to look at my table to help me out with this. So tangent of 60 degrees, I'm looking at tangent 60 degrees, so that's square root 3. So square root 3 minus tangent 30, I'm going to look at tangent and then look at 30. I get square root 3 over 3. Now, if I want to make this into a, where I can put it together, as one fraction, I can multiply this by, remember this is over 1, so I can multiply by 3 over 3. So I get 3 root 3 over 3 minus root 3 over 3. So this would just be 3, let me write this differently. Imagine that this is a 1 right here. So 3 root 3 minus 1 root 3 over 3. Because the root 3's are both there, you can subtract these. So this would become 2 root 3 over 3. I do notice sometimes in trig that people can be a little unsure of when you're allowed to combine radicals together. Adding and subtracting radicals is difficult. They have to, it's almost like you need them as like terms. So if you have the same thing inside of the square roots, then yes, you can put them together like that. Almost kind of treating them like terms. But let's say, I'm just going to do this off to the side. If I said like root 2 minus root 3, I can't do anything with that. It would just stay as it is. Let's do part B. So part B might look confusing to you because it says pi over 6. But remember, pi over 6 is the same as what in degrees? Pi over 6 is 30 degrees. So when I'm saying sine of pi over 6, that's the same as sine of 30 degrees. So sine of 30 degrees, I look at my table, I get 1 over 2. Cosine of 30 degrees, I look at my table, I get square root 3 over 2. I simplify, I get 2 root 3 over 4, which will simplify to root 3 over 2. I'm going to go ahead and go over our next little subsection here. We're going to start using some identities. So this is reciprocal and quotient identities. Alrighty, so I'm going to go ahead and start writing these out. Cosecant of an angle is equal to 1 over sine of that angle. Secant of an angle is 1 over cosine. Cotangent of theta is equal to 1 over tangent theta. You can also swap these around. So you can also write this as sine of theta equals 1 over cosecant theta. Cosine theta equals 1 over secant theta. And tangent theta equals 1 over cotangent theta. So these are what's called your reciprocal identities. Then we have quotient identities. The quotient identities are tangent and cotangent. So tangent theta is equal to sine theta divided by cosine theta. Cotangent theta is equal to cosine theta over sine theta. Let me show you the tangent theta a little bit. So I would pause and just kind of write all this down before you watch this part. But remember that sine is opposite over the hypotenuse, and then cosine is adjacent over the hypotenuse. When you divide fractions like this is the same thing as writing opposite over hypotenuse times hypotenuse over adjacent. You might know it as keep, change, flip. And so these hypotenuses would cancel out, and it leaves you with opposite over adjacent. So that's kind of a little bit of a proof. I mean, it's kind of a bad proof, but a little bit of how we know that tangent is sine over cosine, because it would just simplify to the opposite over adjacent, which we know is tangent. That's just the definition of tangent. So you do need to know all of these. You do need to know them. And they come up for different reasons. Let's go ahead and do a few more examples. So this one, let me see what number we're on. Okay, this will be example 4. I want to use some of these identities for us. This says, given sine of alpha equals 5 over 8, and cosine of alpha equals square root 39 over 8, find tangent theta using identities. Now we have to be careful. If it says use identities, then we want to make sure we use identities. Technically, for this problem, you could use like a triangle. So you could say, okay, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. Let me go ahead and label my triangle. But the point of this question is to use an identity. So if I say I'm looking for tangent of theta, tangent is, sorry, I made a little mistake here. I need the angles to all be the same. So let me go ahead and change that. Sorry, I meant to make them all alpha just because we've been using theta so much. So I was like, let me use alpha instead. But I accidentally still wrote it as theta in my question. Sorry about that. So just make sure you have all your angles for this question as alpha. So tangent of alpha would be sine of alpha over cosine of alpha. Sine of alpha is 5 over 8. Cosine of alpha is square root 39 over 8. So be careful here. Sometimes what students will do is they'll write out sine 5 over 8. And then they'll say cosine square root 39 over 8. And then they feel confused because they're like, I didn't know what to do with the sine and cosine after this. Well, they shouldn't have been there. These are not angles. So you don't want to put them in where the angle goes. The whole thing should be getting replaced. So I'm replacing the whole thing of sine alpha with 5 over 8. So be very careful here, okay? Now I can simplify, so 5 over 8. When you divide by a fraction, you can multiply by its reciprocal. So this would become 5 over square root 39. And we do want to rationalize this, so that would become 5 square root 39 over 39 as my final answer. I've got a few more identities for you. Our next little subsection of identities is called the Pythagorean identities. These are also very important, and you will have to remember them. Your first one says sine squared of an angle, theta, plus cosine squared of theta is equal to 1. So this is cool, right? Because, well, maybe you don't think so right now, but if you plug any angle, it doesn't matter what theta is. If you plug it into sine and then you square it, and you plug it into cosine and then you square it, and then you add it, it will always equal 1. I think that's cool. Let me share with you some notation stuff here. Another way to write this is to say sine of theta squared plus cosine of theta squared equals 1. You do not want to write out sine theta squared plus cosine theta squared equals 1. This is not the same thing. This is saying that you want to square the angle first and then plug it into your function. What we want to do is we want to plug it into our function and then square it. So this is a common notation for the same thing. But it's good to be aware of what it's trying to say. There are some other versions of this identity. So if I start off with, I have sine squared, stop being bold. Stop being bold. Okay. Kinda okay. Sorry, y'all. So if I write out the identity again, remember that in math, we can do whatever we want to something as long as we do it to all sides. If I divide everything in here by cosine squared theta, I'll be left with sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. Simplify this further. Sine over cosine would be tangent, and it's squared, so this becomes tangent squared. Anything over itself is 1, and 1 over cosine is secant, and we'll just using these reciprocal identities up here, and it would be squared. This is a new identity. And it just comes from sine squared plus cosine squared equals 1, but now this one's tangent squared plus 1 equals secant squared. Another identity we can get is we can take the original cosine squared plus sine squared equals 1. And if we divide everything in here by sine squared, I'm not going to write all the work out for this one, but this one would be 1 plus cotangent squared theta equals cosecant squared theta. So this is another identity. This is one of those times where I wouldn't necessarily memorize all 3 of them, but if you know the first one, you can always get to the other 2. of course, we'll do an example using this. So this is example 5. And I'm going to say, given... I know that I might be going fast in this video. Usually I would give a bunch of pauses, if we were actually in class. But you guys can just pause whenever you want to. So just make sure, you pause between so you can just write everything out. I think it would just be a little awkward if I was pausing constantly. So our next little example is given tangent theta equals 12 over 5. Find secant theta using identities. And so again, with this one, I want you to maybe think about for a moment, pause this and just kind of think about what you would even try to do with this. Even if you wouldn't try to use identities, just what would you try at all? I'll tell you another way you can do this, not using identities, is you can say tangent is opposite over adjacent. So that's giving you two sides of the triangle. Secant is your hypotenuse over your adjacent. So if we solve for the hypotenuse, we can go get secant. That's one way to do this problem. Now the point of this one says using identities, so we want to make sure that we use identities here. So I'm going to need an identity that uses tangent and secant in it. And I don't want it to use anything else, trig function wise, because I want to make sure I only have one unknown. So hopefully you can see it right above what we need to use. We're going to use this one right here. So this says tangent squared theta plus 1 equals secant squared theta. So I have tangent theta, so I can plug that in and solve it for secant. Be careful, I am going to rewrite this notation for us, just so we don't get confused. So remember, this is tangent of an angle squared, and this would be secant of my angle squared. So you want to make sure you plug in the entirety. Tangent theta, I'm going to completely replace it here with 12 over 5. I'm not plugging 12 over 5 in as just theta because that's not an angle. It doesn't have a degree symbol and it doesn't have pi. It's not an angle. It's the entirety of tangent at that angle. So if I plug that in here, I get 12 over 5 squared plus 1 equals secant theta squared. Now we're going to simplify, so I get 144 over 25 plus 1 equals secant theta squared. I'll come over here so I don't have to scroll down too much. Remember, anytime you want to add fractions, 1 can be written over 1. Anything can be written over 1 if it isn't a fraction. And I want common denominators, so I'll multiply this by 25 over 25. I get 144 over 25 plus 25 over 25 equals secant theta all squared. Add this together, I get 169 over 25 equals secant theta all squared. Take a square root of both sides. I'm left with 13 over 5 equals secant theta. Now again, this could involve some positives or negatives, but that would depend on maybe if it was in a different quadrant, which I'm not really talking about in this section. I'll talk about it in our next section, what happens if we go to different quadrants. I have one more set of identities to give you, and these are called the co-function identities. These don't really come up yet. They're just kind of stuck in this section, but says sine of theta equals cosine 90 degrees minus theta, and cosine of theta equals sine 90 degrees minus theta. I'm just going to tell you that for my class, you don't need to memorize these. However, it's not a crazy idea. You can kind of see it if you look at the, think about the 30 and 60 for a second. If I say sine of 30 degrees is equal to cosine 90 degrees minus 30 degrees, this is saying that sine of 30 is equal to cosine of 60, which we can see that in our table. If we go back to the table real quick, sine of 30, cosine of 60, yeah, those are equal to each other. So you can kind of see that's a little bit of an example of it happening. I don't think it would be crazy for me to ask you to memorize it, but I'll just let you know that it's not a super common thing that we're going to be using. So I wouldn't worry about it too much. Alrighty, so that is it for 5.2. I know that was a little bit of a longer section, and you may need to you might have to pause for a lot in this one. So thank you for sticking with it, and as always, if you have any questions, you feel free to let me know. I will see y'all in our next video. I hope y'all have a wonderful day. Bye-bye.